The telegram arrived at the patent office in Bern on a Thursday morning in March 1905. Though it contained no news of the sort that would typically merit such urgency, and the young clerk who received it, a man whose hair already showed signs of the wild disarray that would later become his trademark, barely glanced at it before returning to the stack of patent applications that had accumulated on his desk like sediment layers in geological time. Albert Einstein did not yet know that the equations he had been scribbling in stolen moments between evaluating designs for electromagnetic regulators would unravel the very fabric of reality itself, that the notions of space and time humanity had carried since Aristotle first walked the Lyceum would prove to be mere approximations, shadows cast on a cave wall by a deeper, stranger truth. The city of Bern in that early spring carried the scent of melting snow and coal smoke, the streets still muddy from winter's retreat, and in the coffee houses where intellectuals gathered beneath gaslight chandeliers, conversations turned to the questions that haunted physics at the dawn of the 20th century. Why did light behave so strangely in the experiments of Michelson and Morley? Why did Maxwell's equations seem to privilege no particular reference frame? Why did the universe appear to whisper secrets in mathematical language that human intuition could not quite grasp? Einstein's apartment on Kramgasse was modest, the rent a significant portion of his salary, and his wife Mileva often worked through the night on calculations while their infant son slept fitfully in the adjacent room. The scratch of pen on paper the only sound besides the occasional clatter of a late carriage on cobblestones below. What Einstein could not have known, what no one could have known, was that the concept he was approaching would render meaningless the very notion of simultaneity. That two events occurring at the same time in one frame of reference might be separated by hours or years in another. That time itself was not the universal river flowing uniformly forward that Newton had imagined, but rather a dimension inextricably woven with the 3 dimensions of space into a 4-dimensional continuum that would come to be called Spacetime. The intellectual journey toward this revelation had begun decades earlier, though its participants did not recognize the destination toward which they travelled. James Clerk Maxwell, working in his study at Glenlair in the Scottish countryside during the 1860s, had unified electricity and magnetism into a single theoretical framework, his equations predicting that electromagnetic waves would propagate through space at a specific velocity, a velocity that, when calculated, matched precisely the measured speed of light. This coincidence was too perfect to be accidental, and Maxwell understood that light itself must be an electromagnetic phenomenon. But his equations contained a peculiarity that troubled physicists for the next 40 years. They did not change form depending on the observer's state of motion, suggesting that the speed of light remained constant regardless of how fast one travelled toward or away from its source. This seemed absurd, violating the common sense understanding that velocities should add together. If you run toward a thrown ball, it approaches you faster than if you stand still. Yet the mathematics insisted otherwise with an almost arrogant certainty. The scientific establishment, wedded to the concept of the luminiferous ether, that invisible substance supposedly permeating all of space through which light waves propagated like sound through air, attempted to preserve the Newtonian framework by proposing that Maxwell's equations only held true for observers at rest relative to this ether. Albert Michelson, a Prussian-born physicist working in Cleveland, Ohio, had developed an interferometer of unprecedented precision specifically to detect Earth's motion through this hypothetical ether, reasoning that as our planet orbited the Sun, we should observe variations in the speed of light depending on whether we measured it parallel or perpendicular to our orbital direction. Together with Edward Morley, he conducted the experiment in 1887 in a basement laboratory, the interferometer floating on a pool of mercury to isolate it from vibrations, and the result shook physics to its foundations. No variation whatsoever could be detected. Earth's motion through the ether, if such a substance existed, was completely undetectable. the speed of light appeared to be precisely constant in all directions, regardless of the planet's motion. George Fitzgerald in Dublin and Hendrik Lorentz in Leiden independently proposed a desperate solution. Perhaps objects physically contracted in their direction of motion through the ether, and perhaps time itself flowed at different rates for moving observers, with these changes conspiring in exactly the right proportions to make the ether forever undetectable. The mathematics worked. Lorentz developed transformation equations describing precisely how lengths and time intervals should change. But the physical mechanism remained mysterious ad hoc, a patch applied to a theoretical framework that was clearly showing cracks. Henri Poincaré in Paris pushed these ideas further, recognizing that the principle of relativity, the notion that the laws of physics should be the same in all uniformly moving reference frames, might be fundamental, but he could not quite bring himself to abandon the ether entirely, could not quite make the conceptual leap that was required. That leap would come from the patent clerk in Bern, the man who'd been expelled from gymnasium in Munich for his rebellious attitude, who'd failed his first attempt at the entrance examination for the Zurich Polytechnic, who had been unable to secure an academic position after graduation, and had settled for evaluating patent applications to pay his rent. Einstein approached the problem not as an experimentalist. He had no laboratory, no equipment, no funding, but as a pure theorist armed only with thought experiments and an almost reckless faith in mathematical consistency. He imagined riding alongside a beam of light, matching its velocity, and asked himself what he would see. Maxwell's equations suggested he should observe a static electromagnetic wave, frozen in place, but no such solution existed in Maxwell's theory. This contradiction convinced Einstein that either Maxwell was wrong, unlikely given the experimental confirmation of his predictions, or the very concepts of space and time were wrong. The paper Einstein composed that summer, while working full-time at the patent office, bore the understated title On the Electrodynamics of Moving Bodies, and it appeared in the September 1905 issue of Annalen der Physik without fanfare, without any indication that it represented a revolution comparable to Copernicus, displacing Earth from the centre of the cosmos. The text began with a remarkable clarity, identifying the asymmetries in the then current understanding of electromagnetic induction that suggested the theoretical framework was incomplete, then proceeding to lay out two postulates from which everything else would follow. First, that the laws of physics are the same in all inertial reference frames, and second, that the speed of light in vacuum is constant regardless of the motion of the light source. From these assumptions alone, armed with nothing more than algebra and careful reasoning about the synchronization of clocks, Einstein derived transformations identical to those Lorentz had proposed, but with a crucial difference. These were not physical effects caused by motion through the ether, but rather revealed the true nature of space and time themselves. Simultaneity was relative. Events that appeared to occur at the same moment to one observer might occur at different times to another observer in motion relative to the first. Time dilation was not an artifact of some mechanical compression of clocks, but rather a fundamental feature of time itself. A clock in motion relative to an observer would genuinely run slower than a clock at rest, not because of any mechanical effect, but because time itself passed more slowly. Length contraction was similarly fundamental. A moving object was genuinely shorter in its direction of motion, not because it was compressed by the ether wind, but because the very geometry of space depended on the observer's state of motion. These were not mere appearances or optical illusions. They were the actual nature of reality, revealed by taking seriously the principle that the laws of physics should not depend on uniform motion. The implications cascaded outward like ripples from a stone dropped into a still pond. If time and space were relative depending on the observer's motion, then they could not be separate independent entities, but must be unified into a single four-dimensional continuum. This insight came not from Einstein initially, but from Hermann Minkowski, who had been Einstein's mathematics professor at the Zurich Polytechnic, and had considered the young student lazy and inattentive. In a 1908 lecture in Cologne, Minkowski declared that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Minkowski reformulated special relativity in geometric terms, treating time as a fourth dimension mathematically similar to the three spatial dimensions, but with a crucial distinction. Distances in space are always positive, but the distance in time enters the equations with an opposite sign, creating a geometry that is hyperbolic rather than Euclidean. In this four-dimensional space-time, events are represented as points, and the history of a particle is a curve called a world line. The separation between two events can be classified as time-like if they can be connected by a signal travelling slower than light, space-like if the connection would require faster-than-light travel, or light-like if light itself could connect them. This geometric framework revealed that what changes under a Lorentz transformation is merely the division of space-time into space and time, just as what changes when you rotate a two-dimensional coordinate system is the division of a vector into x and y components, but the vector itself, the geometric object, remains unchanged. The space-time interval between two events, a quantity combining both spatial separation and temporal separation, remains invariant across all reference frames, and this interval represents the true geometric relationship between events in a way that neither spatial distance alone nor temporal separation alone can capture. Einstein himself initially dismissed Minkowski's geometric reformulation as unnecessary mathematical complication, but he would soon discover that this framework was precisely what he needed to extend his principle of relativity beyond the restricted case of uniform motion. Special relativity, for all its revolutionary implications, only addressed observers moving at constant velocities relative to one another, but the universe is filled with accelerations, planets orbiting stars, apples falling from trees, rockets burning fuel to change course. Einstein became convinced that a truly comprehensive theory must not distinguish between accelerated and unaccelerated motion, that the laws of physics should be the same in all reference frames regardless of their acceleration. This pursuit would consume the next decade of his life, transforming him from a patent clerk publishing in his spare time to a professor in Zurich, then Prague, then back to Zurich at the Polytechnic, then finally to Berlin as a member of the Prussian Academy of Sciences, freed from teaching duties to focus entirely on research. The breakthrough that guided him was the equivalence principle, the recognition that there was no local experiment that could distinguish between the effects of gravity and the effects of acceleration. Standing in an elevator on Earth's surface, you feel pressed against the floor by gravity. But if the elevator were instead far from any gravitational source, but accelerating upward at 9.8 meters per second squared, you would feel exactly the same sensation. No measurement confined to the elevator could tell you which situation you were actually in. This equivalence, which Einstein later called the happiest thought of his life, suggested that gravity was not truly a force at all in the Newtonian sense, but rather something to do with the geometry of space-time itself. If space-time could be warped, curved, distorted from the flat geometry Minkowski had described, then objects following straight paths through this curved space-time would appear to accelerate from the perspective of someone thinking in terms of three-dimensional space and separate time. Einstein sought the mathematical equations that would describe how matter and energy curve space-time, and how this curvature affects the motion of matter and light. The mathematics required, tensor calculus, differential geometry, Riemannian manifolds, was far beyond what he had learned as a student, and he struggled through years of false starts and blind alleys, consulting with mathematicians including his old classmate Marcel Grossmann, who introduced him to the work of Gregorio Ricci Curbastro and Tullio Levi-Civita on tensor analysis. The technical challenges were formidable, Einstein needed equations that would be generally covariant, maintaining their form in any coordinate system, that would reduce to Newtonian gravity in the limit of weak fields and slow velocities, that would conserve energy and momentum, and that would be consistent with special relativity in regions of spacetime far from any gravitating mass. By November 1915, racing in competition with the mathematician David Hilbert, who was approaching the same goal from a different direction, Einstein finally arrived at the field equations of general relativity, 10 coupled nonlinear partial differential equations relating the curvature of spacetime at each point to the distribution of matter and energy at that point. The equation could be written compactly as Gn, Scarcius ATTM, where Gem represents the Einstein tensor encoding the curvature of spacetime, and Tm represents the stress-energy tensor, describing the distribution of matter, energy, momentum, and stress. The physicist John Wheeler would later summarize the content with elegant brevity. Spacetime tells matter how to move, and matter tells spacetime how to curve. The predictions of general relativity were stranger than those of special relativity by an order of magnitude. Not only were space and time relative and unified, but their very geometry was dynamic, responsive to the presence of mass and energy. Near a massive object like the Sun, spacetime curves, and this curvature affects not just the motion of material objects like planets, but also the propagation of light itself. Light beams passing near the Sun should bend, deflected by the curvature of spacetime by an amount twice as large as Newtonian gravity would predict if light were treated as consisting of massive particles. Time should run slower in stronger gravitational fields, so a clock on Earth's surface should tick more slowly than an identical clock far from Earth, not because of any mechanical effect, but because time itself flows at different rates at different locations in curved spacetime. The orbit of Mercury, the innermost planet, whose perihelion had been observed to precess slightly more than Newtonian gravity, could account for, even after considering the gravitational influences of all other planets, should exhibit exactly the anomalous precession general relativity predicted without any adjustable parameters or hidden masses. This last prediction was particularly significant because the data already existed. Einstein did not predict a new phenomenon to be discovered, but rather explained an existing anomaly, and when his calculations matched the observed 43 arc-seconds per century of unexplained precession, he later wrote that he had palpitations of the heart, that something actually snapped inside him. But it was the prediction about light deflection that would capture the world's imagination and transform Einstein from an obscure theoretical physicist, known only to specialists, into an international celebrity whose face would become synonymous with genius itself. Arthur Eddington, Secretary of the Royal Astronomical Society in London, and a Quaker conscientious objector during the Great War, learned of Einstein's theory through Dutch intermediaries, despite the barriers that the war had erected between British and German science. Eddington became one of general relativity's earliest champions, recognizing both its mathematical elegance and its testability. The deflection of starlight passing near the Sun could only be measured during a total solar eclipse, when the Sun's glare was blocked and stars near its edge became visible. Calculating backward from Einstein's predicted deflection angle, Eddington identified the total solar eclipse of May 29, 1919, as an ideal opportunity. The Sun would be positioned in front of the Hyades cluster, providing numerous bright stars near its limb whose positions could be measured and compared with photographs of the same star field taken months earlier when the Sun was in a different part of the sky. Eddington organised 2 expeditions, one to Sobral in Brazil led by Andrew Crommelin, and one to the island of Principe off the coast of West Africa, which Eddington himself led, both locations lying in the path of totality. The Principe expedition faced clouds during much of the eclipse, and only a few usable photographic plates were obtained, but these showed a deflection consistent with Einstein's prediction of 1.75 arc-seconds and inconsistent with the Newtonian prediction of 0.7 arc-seconds. The Sobral expedition obtained clearer photographs though issues with one of their telescopes complicated the analysis, but their best data also supported Einstein. The announcement of these results at a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6, 1919, occurred against the backdrop of a Europe still reeling from the war that had killed millions, and the fact that British scientists had confirmed the theory of a German physicist was widely interpreted as a sign of hope, a demonstration that science transcended national boundaries and could help heal the wounds of conflict. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown," and overnight Einstein became famous in a way that few scientists before or since have experienced, his photograph appearing in newspapers worldwide, his name becoming a synonym for intellectual brilliance. Yet for all the public fascination with general relativity, the theory remained extraordinarily difficult to work with mathematically, its non-linear equations admitting exact solutions only in highly symmetric special cases. The first exact solution, discovered by Karl Schwarzschild in 1916 while serving in the German army on the Russian front, described the space-time geometry around a spherically symmetric non-rotating mass. Schwarzschild sent his solution to Einstein from the trenches, dying of pemphigus only months later, and Einstein presented Schwarzschild's work to the Prussian Academy. The Schwarzschild solution revealed a troubling feature. At a particular radius, now called the Schwarzschild radius, the mathematical expressions appeared to become singular, with certain components of the metric going to infinity and others to zero. For a mass equal to the Sun's mass, this radius was about 3 kilometers, far smaller than the Sun's actual radius of 700,000 kilometers, so it seemed merely a mathematical curiosity, not a physical reality. For decades, physicists debated whether this singularity was a real feature of the solution, or merely an artifact of the particular coordinate system Schwarzschild had chosen. The resolution, which emerged gradually through work by Georges Lemaitre, Arthur Eddington, David Finkelstein, and others, was that the singularity at the Schwarzschild radius was indeed a coordinate artifact. Space-time there was not truly singular, but something remarkable nevertheless occurred at that location. It represented a point of no return, a boundary such that anything crossing inward could never escape, not even light itself. These regions would eventually be called black holes, though that term would not be coined until 1967 by John Wheeler. The concept of a black hole pushed the strangeness of space-time to an extreme that tested the limits of human intuition. Near the Schwarzschild radius, space-time is so severely warped that the roles of time and space are effectively interchanged. The radial direction becomes time-like, meaning that falling inward becomes as inevitable as moving forward in time is elsewhere in the universe. An observer falling across the event horizon would notice nothing special at the moment of crossing. No barrier or discontinuity, just an inexorable pull toward the centre that cannot be resisted by any amount of thrust or effort. But to a distant observer watching this descent, the falling observer would appear to slow down asymptotically as they approach the horizon, their clock appearing to tick more and more slowly, the light they emit becoming increasingly redshifted until they fade from view without ever actually appearing to cross the horizon. Both perspectives are equally valid. They are simply different ways of slicing space-time into space and time, and the coordinate-independent reality is that the infalling observer does cross the horizon in their own finite proper time, while remaining eternally frozen at the horizon in the time coordinate of the distant observer. At the true singularity at the centre, where the Schwarzschild radius goes to zero, the curvature becomes infinite, and general relativity itself breaks down, signalling that a more complete theory incorporating quantum mechanics is needed to describe what happens there. For most of the 20th century, black holes were considered theoretical curiosities, mathematically interesting but probably not existing in nature. Yet observations beginning in the 1960s of X-ray sources like Cygnus X1, quasars powered by supermassive black holes at galactic centres, and eventually gravitational waves from merging black holes, would establish that they are not only real, but abundant throughout the universe. The dynamic nature of space-time implied by general relativity had another profound consequence that Einstein himself initially resisted. The universe as a whole could not be static. If space-time curves in response to matter and energy, and if matter and energy are distributed throughout the universe, then the geometry of the universe itself must either be expanding or contracting. When Einstein applied his field equations to cosmology in 1917, assuming for simplicity that the universe was homogeneous and isotropic on large scales, the same in all places and all directions, he found that his equations did not permit a static solution. Rather than accept that the universe might be dynamic, Einstein modified his equations by adding a term called the cosmological constant, represented by L, which acted as a kind of repulsive gravity that could balance the attractive gravity of matter and hold the universe in a static state. This modification was mathematically permissible. The equations with the cosmological constant still satisfied the requirement of general covariance, but it was physically ad hoc, introduced solely to achieve a desired outcome. Meanwhile, in Russia, Alexander Friedmann was studying the Einstein field equations without the cosmological constant and without assuming a static universe, and he found solutions describing universes that expanded or contracted depending on their matter content and initial conditions. Friedmann's work, published in 1922, was initially dismissed by Einstein as a mathematical exercise without physical significance, but Georges Lemaitre, a Belgian priest and physicist, independently discovered similar solutions and went further, proposing in 1927 that if the universe is currently expanding, then extrapolating backward in time it must have been smaller and denser in the past, eventually reaching a state of extreme density that he called the primeval atom, the beginning of space and time themselves. The observational evidence that would vindicate Friedmann and Lemaitre was already being gathered by astronomers studying the spectra of nebulae, fuzzy patches of light that might be clouds within our own Milky Way galaxy, or might be separate galaxies in their own right. Vesto Slipher at Lowell Observatory in Arizona had measured the spectra of numerous spiral nebulae and found that the vast majority showed redshifts. Their spectral lines shifted toward longer wavelengths in a manner consistent with them moving away from Earth. Edwin Hubble, working with the 100-inch telescope at Mount Wilson Observatory in California, resolved individual stars in some of these nebulae and identified Cepheid variables whose brightness fluctuations allowed him to measure their distances, establishing definitively that they were indeed separate galaxies far beyond the Milky Way. In 1929, Hubble compiled distance measurements for a sample of galaxies along with Slipher's velocity measurements and discovered a relationship. The farther away a galaxy was, the faster it was receding, with the recession velocity proportional to distance. This Hubble's law was exactly what one would expect if space itself were expanding uniformly, carrying galaxies along with it like raisins in a rising bread dough. The expansion was not galaxies moving through space away from some central point, but rather space itself expanding everywhere, increasing the distances between galaxies. Einstein, upon learning of Hubble's observations, reportedly called the introduction of the cosmological constant his biggest blunder, though accounts differ on whether he actually used those exact words. The universe, it appeared, had a history, a beginning and evolution, and space-time was not merely a stage on which events played out, but an active participant, expanding and carrying the matter and energy of the universe along with it. The expanding universe raised urgent questions about the nature of space-time on the largest and smallest scales. If we extrapolate the expansion backward in time, we reach a moment some finite time in the past when all the matter and energy in the universe was compressed into an infinitesimal volume at infinite density and temperature, a singularity similar in character to the one at the centre of a black hole but encompassing the entire universe. This moment, which Fred Hoyle mockingly called the Big Bang during a BBC radio broadcast in 1949, though the name stuck despite his intention to disparage the idea represented the beginning of space-time itself. There was no before the Big Bang in any meaningful sense because time itself began at that moment. Asking what came before is like asking what is north of the North Pole, a question that presupposes a coordinate system that does not extend that far. Roger Penrose and Stephen Hawking proved, through rigorous mathematical theorems in the 1960s, that singularities were not artifacts of special symmetric cases, but were generic features of general relativity under very general conditions. Any collapsing matter whose density and pressure satisfied certain reasonable conditions must form a singularity, and the universe itself must have emerged from a singularity if it is currently expanding. These singularity theorems indicated that general relativity contained the seeds of its own destruction, predicting conditions under which its own assumptions broke down, and pointing toward the necessity of a quantum theory of gravity. The quantum nature of reality, established in the early 20th century through the work of Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others, seemed fundamentally incompatible with the smooth, continuous geometry of space-time in general relativity. Quantum mechanics described the microscopic world as inherently probabilistic, with particles exhibiting wave-particle duality, with measurement unavoidably disturbing the system being measured, with uncertainty relations limiting the precision with which certain pairs of variables like position and momentum could be simultaneously known. Quantum field theory, which emerged in the 1930s and reached its mature form in the 1950s and 1960s, described particles as excitations of underlying quantum fields permeating space-time, with these fields subject to violent quantum fluctuations at sufficiently small scales. But all of this quantum physics was formulated in a fixed space-time background, assuming that space-time itself provided a non-dynamic stage on which quantum phenomena occurred. General relativity, conversely, treated space-time as a dynamic, classical field, curving in response to matter and energy, but not subject to quantum uncertainty. The contradiction between these two foundational theories of 20th century physics, quantum mechanics and general relativity, one governing the very small and one governing the very large, represented perhaps the deepest unsolved problem in theoretical physics, and resolving it required understanding the quantum nature of spacetime itself. At the Planck scale, defined by a characteristic length of about 10 ⁻³ 35 meters, a time of about 10 ⁻⁻�43 seconds, and an energy of about 10 molu 19 GeV, quantum fluctuations of spacetime should become so violent that the classical concept of a smooth geometric manifold loses meaning. Just as electromagnetic fields fluctuate at the quantum level, with virtual particle-antiparticle pairs constantly appearing and annihilating in the vacuum, spacetime itself should fluctuate, with the geometry writhing and churning in a quantum foam of microscopic black holes forming and evaporating, wormholes opening and closing, topology changing moment by moment in ways that defy visualization. No experiment can directly probe such scales. The energies required are far beyond any conceivable particle accelerator, but theoretical considerations and thought experiments provide tantalizing hints. In 1974, Stephen Hawking discovered through a remarkable calculation combining quantum field theory with general relativity that black holes are not entirely black. Quantum effects near the event horizon cause them to emit thermal radiation, with a temperature inversely proportional to their mass. This Hawking radiation means that black holes slowly evaporate, losing mass over time, and for small black holes this evaporation can be rapid. A black hole with the mass of a mountain would have a Schwarzschild radius smaller than an atomic nucleus, and would evaporate in a flash of gamma rays in less than a second. This discovery established that black holes have thermodynamic properties, with an entropy proportional to the area of their event horizon, and this black hole entropy suggests a deep connection between gravity, quantum mechanics, and information theory that remains not fully understood. The quest to reconcile quantum mechanics with general relativity to formulate a quantum theory of gravity has pursued multiple paths. One approach, called loop quantum gravity, attempts to quantize spacetime directly, proposing that space at the Planck scale consists of discrete quantum elements, loops, and nodes forming a network analogous to how matter is composed of atoms rather than being continuous. In this picture, space is granular at the smallest scales, and time emerges from the quantum dynamics of these spatial networks. Another approach, string theory, abandons the notion of point particles entirely, proposing instead that the fundamental constituents of reality are one-dimensional extended objects, strings, whose different vibrational modes correspond to different particles. String theory requires space-time to have more than 4 dimensions, typically 10 or 11, with the extra dimensions compactified, curled up on scales so small that they have not been detected. String theory naturally incorporates gravity, with one particular vibrational mode of the string corresponding to the graviton, the hypothetical quantum of the gravitational field, and it has produced remarkable mathematical insights, including the holographic principle suggesting that all the information in a volume of space can be encoded on its boundary, like a hologram. Yet string theory has also faced criticism for making few testable predictions, and for existing in a vast landscape of possible vacuum states, leading to questions about whether it truly constitutes a scientific theory in the Popperian sense of being falsifiable. Regardless of which approach to quantum gravity ultimately proves correct, certain features of space-time at the quantum level seem robust. The notion of a definite space-time geometry becomes meaningless at the Planck scale. Instead, one must speak of superpositions of geometries, quantum uncertainty in the very fabric of space-time. Causality itself becomes fuzzy, with quantum fluctuations potentially creating closed time-like curves that loop back on themselves, raising all the paradoxes associated with time travel. The question of what it means for an event to occur at a particular location at a particular time loses its sharpness when space and time themselves are subject to quantum uncertainty. These considerations have led some physicists to suggest that space-time is not fundamental at all, but rather emergent, arising from some deeper, more fundamental structure in the way that temperature emerges from the statistical behavior of atoms, or in the way that the smooth surface of a fluid emerges from the chaotic motion of molecules despite being composed of discrete particles. If space-time is emergent, then what is the underlying structure from which it emerges? Proposals have included quantum entanglement patterns, with the geometric connectivity of space-time arising from quantum correlations between degrees of freedom, quantum information, with space-time geometry encoding the relationships between bits of information, and various algebraic or combinatorial structures that bear no resemblance to anything we can visualize spatially. These ideas remain highly speculative, explored through mathematical models and thought experiments, but they represent a willingness to question even the most basic assumptions about the nature of reality. Experimental tests of space-time structure, though challenging, have become increasingly sophisticated. The prediction of general relativity that gravitational fields cause time dilation has been confirmed with exquisite precision using atomic clocks. First in the Pound-Rebka experiment of 1959 using gamma-ray photons climbing a tower at Harvard, and more recently with optical lattice clocks sensitive enough to detect time dilation over elevation differences of a single centimetre. The Global Positioning System, a network of satellites orbiting Earth and broadcasting timing signals that receivers use to determine their position, must account for both special relativistic time dilation due to the satellite's orbital velocity and general relativistic time dilation due to the difference in gravitational potential between the satellites and receivers on Earth's surface. Failure to include these corrections would cause position errors accumulating at a rate of kilometers per day. gravitational lensing, the bending of light by massive objects predicted by general relativity, has been observed in countless instances, from Einstein rings where a distant galaxy is lensed into a nearly perfect circle by an intervening galaxy cluster, to the gravitational microlensing of stars in our galaxy by dark compact objects passing in front of them, to the weak lensing correlations used to map the distribution of dark matter across the universe. The direct detection of gravitational waves by the LIGO and Virgo observatories, beginning with the observation of a binary black hole merger in September 2015, opened an entirely new window on the universe, allowing us to observe spacetime itself vibrating, ripples spreading outward from violent events at nearly the speed of light and carrying information about the merger dynamics, encoded in the amplitude and frequency evolution of the gravitational wave signal. These gravitational wave observations confirmed predictions of general relativity in the strong field, dynamical regime previously inaccessible to testing, demonstrating that black holes of the masses predicted by stellar evolution theory do indeed exist, that they can merge on observable timescales, that the ring down of the merged black hole follows the spectrum of quasi-normal modes predicted by black hole perturbation theory, and that gravitational waves propagate at the speed of light to within 1 part in 10^15, as constrained by the near-simultaneous observation of gravitational waves and electromagnetic radiation from a neutron star merger in August 2017. The observation of this neutron star merger, designated GW1SM7 or AGAS-17, was particularly remarkable because telescopes across the electromagnetic spectrum observed the explosion in its afterglow, witnessing the synthesis of heavy elements like gold and platinum in the neutron-rich ejecta, confirming that at least some of the heaviest elements in the periodic table are forged in these cataclysmic events. The gravitational wave signal from the inspiral phase allowed precise measurement of the star's tidal deformability, constraining the equation of state of matter at nuclear densities and providing information about the physics of neutron stars that cannot be obtained in any terrestrial laboratory. Future gravitational wave detectors, including space-based observatories like LISA, the Laser Interferometer Space Antenna planned for launch in the 2030s, will observe lower frequency gravitational waves from supermassive black hole mergers in distant galaxies, from the inspiral of stellar mass compact objects into supermassive black holes, and potentially from exotic sources like cosmic strings or phase transitions in the early universe, while pulsar timing arrays, which monitor the arrival times of radio pulses from an array of a millisecond pulses scattered across the galaxy, are sensitive to the very low-frequency gravitational wave background produced by the population of supermassive black hole binaries throughout the universe, or by processes in the very early universe. The realization that space-time itself has a history, that it emerged from the Big Bang and has been expanding and evolving ever since, raises profound questions about initial conditions and fine-tuning. Why did the universe begin in a state of extraordinarily low entropy, since the second law of thermodynamics says that entropy increases over time? So starting with low entropy was necessary to allow for the entropy increase we observe. Why is the universe so homogeneous and isotropic on large scales, despite the fact that regions separated by more than the horizon distance at early times, the maximum distance light could have travelled since the Big Bang, could not have been in causal contact and thus should not have had any reason to have the same temperature and density? These puzzles motivated the development of inflation theory in the early 1980s, pioneered by Alan Guth, Andrei Lindy, Alexei Starobinsky and others, which proposes that the very early universe underwent a brief period of exponential expansion, driven by the energy density of a quantum field in a metastable state. This inflationary expansion would have smoothed out any initial inhomogeneities, stretched the observable universe from a causally connected patch much smaller than the horizon at the time, and left behind quantum fluctuations in the inflaton field that were stretched to cosmic scales and seeded the density perturbations that eventually grew into galaxies and large-scale structure. Inflation makes specific predictions about the statistical properties of these primordial perturbations, that they should be nearly scale invariant, Gaussian, and adiabatic, and observations of the cosmic microwave background radiation by satellites like COBE, WMAP, and Planck have confirmed these predictions with impressive precision, lending strong support to the inflationary paradigm, even though many details remain uncertain and many different models of inflation fit the current data. The cosmic microwave background itself provides a snapshot of the universe as it was about 380,000 years after the Big Bang, when the expanding and cooling plasma of electrons, protons, helium nuclei, and photons finally became cool enough for electrons and nuclei to combine into neutral atoms, allowing photons to travel freely rather than being constantly scattered by free electrons. These photons have been travelling through space ever since, their wavelengths stretched by the expansion of spacetime from visible light to microwaves, and they reach us from all directions, forming a nearly uniform glow at a temperature of 2.725 Kelvin, with tiny variations of a few parts in a 100,000 across the sky. These temperature variations, imprinted on the cosmic microwave background by the density fluctuations in the early universe, contain a wealth of information about cosmological parameters, the geometry of space-time on the larger scales, the composition of the universe, the amplitude and spectrum of primordial perturbations, the age of the universe. The pattern of variations, when decomposed into spherical harmonics, shows acoustic oscillations corresponding to sound waves that propagated through the primordial plasma before recombination, compressions and rarefactions driven by the competition between gravitational attraction and radiation pressure, and the detailed structure of these acoustic peaks allows cosmologists to determine that the universe is spatially flat to within about 1%, that it is composed of roughly 5% ordinary matter, 27% dark matter, whose nature remains unknown, and 68% dark energy, whose properties remain deeply mysterious. Dark energy, the component driving the accelerated expansion of the universe discovered in 1998 through observations of distant type Ia supernovae, represents perhaps the most profound puzzle in contemporary physics. Einstein's cosmological constant, which he introduced and then abandoned, has made a surprising comeback as the simplest explanation for dark energy, with the vacuum of space carrying an intrinsic energy density that gravitates repulsively, causing the expansion to accelerate rather than decelerate as ordinary matter and radiation would cause. Yet if dark energy is indeed vacuum energy, its measured value is absurdly small compared to theoretical expectations from quantum field theory, differing by some 120 orders of magnitude in what has been called the worst prediction in the history of physics. This cosmological constant problem suggests that either our understanding of quantum field theory is profoundly incomplete, or there is some unknown symmetry or principle that cancels the vacuum energy contributions to extraordinary precision, but not exactly, or we are observing a selection effect related to the conditions necessary for intelligent observers to exist. Anthropic reasoning of this sort, that we observe the universe to have properties compatible with our existence because otherwise we would not be here to observe it, is controversial as it seems to abandon the search for a dynamical explanation. But in the context of eternal inflation or the string theory landscape, where different regions of spacetime or different vacuum states can have different values of physical parameters, including the cosmological constant, anthropic selection may play a role in explaining otherwise arbitrary-seeming features of our observable universe. The large-scale structure of the universe, the distribution of galaxies and galaxy clusters and voids, forming a cosmic web of filaments and sheets, represents the outcome of gravitational instability acting on the initial perturbations seeded by inflation, with dark matter playing a crucial role in amplifying these perturbations during the matter-dominated era before dark energy came to dominate. N-body simulations tracking the gravitational interactions of billions of dark matter particles from the early universe to the present reproduce the observed large-scale structure with remarkable fidelity, allowing detailed tests of cosmological models and constraints on alternative theories of gravity. These simulations reveal that dark matter halos, the gravitationally bound structures within which galaxies form have a characteristic density profile and substructure population, and while some discrepancies between simulation predictions and observations of small-scale structure remain, the core cusp problem, the missing satellites problem, the too big to fail problem, it is unclear whether these represent failures of the cold dark matter paradigm or rather reflect the complex astrophysics of galaxy formation, involving baryonic processes like gas cooling, star formation, and feedback from supernova and active galactic nuclei that are difficult to simulate accurately. The motion of stars and gas in galaxies, the velocity dispersions of galaxies in clusters, the gravitational lensing of background galaxies by foreground matter, and the temperature and spatial distribution of hot X-ray emitting gas in galaxy clusters all provide independent evidence for dark matter. Yet its particle nature remains elusive, despite decades of increasingly sensitive direct detection experiments searching for the scattering of dark matter particles off atomic nuclei in deep underground detectors shielded from cosmic rays, and despite searches for the annihilation or decay of dark matter, particles producing gamma rays, neutrinos, or antimatter cosmic rays that would stand out against astrophysical backgrounds. The possibility that modifications to general relativity rather than dark matter might explain galactic rotation curves and other observations has been extensively explored, with modified Newtonian dynamics, or MOAND, achieving some empirical success in fitting rotation curves with a single adjustable parameter, but attempts to construct a relativistic theory underlying MOND that also explains cosmological observations and gravitational lensing have encountered severe difficulties, and the observation that the Bullet Cluster, a system of two colliding galaxy clusters, shows a clear spatial separation between the location of most of the baryonic matter as traced by X-ray emission and the location of most of the gravitating mass as traced by weak gravitational lensing, provides compelling evidence for dark matter as a distinct component that passed through largely unaffected by the collision, while the gas experienced drag forces and was slowed. Nevertheless, the failure to detect dark matter particles despite intensive efforts, and the growing catalogue of astrophysical puzzles at small scales keep alternative theories alive as areas of ongoing research, reminding us that our understanding of space-time and gravity might still be incomplete, even in regimes we thought were well understood. The possibility of extra dimensions, a staple of string theory, offers another route to modifying gravity. If our four-dimensional space-time is embedded in a higher dimensional space, gravity might propagate through the extra dimensions, while ordinary matter is confined to a four-dimensional brane, leading to deviations from general relativity at specific scales, depending on the size and shape of the extra dimensions. Laboratory tests of Newton's inverse square law at sub-millimeter distances, precision measurements of gravitational waves, and searches for Kaluza-Klein graviton modes in particle colliders all constrain but have not ruled out various extra-dimensional scenarios. Time travel, a concept that captivates the popular imagination and has been a staple of science fiction for over a century, has a complicated status in general relativity. The theory permits solutions containing closed time-like curves, world lines that loop back on themselves such that an observer following such a curve would return to an earlier point in their own past. The Gödel metric, discovered by the logician Kurt Gödel in 1949 as a solution to Einstein's field equations, describes a rotating universe containing closed time-like curves passing through every event, though observations establish that our actual universe does not rotate in the manner required by Gödel's solution. The Kerr metric, describing a rotating black hole, contains closed time-like curves within the inner horizon, though reaching them would require surviving the infinite tidal forces at the Cauchy horizon, where predictability breaks down. Traversable wormholes, hypothetical tunnels connecting distant regions of space-time or even different universes, could potentially be converted into time machines through a process involving differential time dilation. though all known wormhole solutions require exotic matter with negative energy density to hold the throat open. And quantum field theory suggests that while quantum states can have negative energy density locally and temporarily, the amount and duration are severely constrained by quantum inequalities. These time machine solutions face additional obstacles from the Hawking chronology protection conjecture, which proposes that the laws of physics prevent the formation of closed time-like curves except possibly on microscopic scales, with semi-classical calculations suggesting that vacuum fluctuations would become infinite on the Cauchy horizon, destroying the time machine before it could be activated, though a full understanding requires the elusive quantum theory of gravity. Even setting aside the question of physical realizability, time travel to the past raises logical paradoxes, most famously the grandfather paradox, in which a time traveller prevents their own birth, leading to apparent contradictions that have generated a vast literature on the consistency of causal loops, the Novikov self-consistency principle, and the possibility of branching timelines in quantum mechanics. The arrow of time, the fact that time has a direction, and that we remember the past but not the future, that eggs scramble but do not unscramble, that entropy increases, remains one of the deepest mysteries relating to space-time. The fundamental laws of physics, whether classical mechanics, electromagnetism, quantum mechanics, or general relativity, are time reversal symmetric or nearly so, showing no fundamental preference for one time direction over the other, yet our experience of time is profoundly asymmetric. This puzzle was recognized by Ludwig Boltzmann in the 19th century and remains not entirely resolved. The thermodynamic arrow of time, the direction in which entropy increases, appears to point from the Big Bang toward the future, but why did the universe begin in such a low entropy state? Roger Penrose has calculated that the probability of randomly selecting initial conditions compatible with our observed universe is absurdly small, roughly 1 part in 10^10 tet 123, a number so large it defies comprehension, suggesting that some principle or mechanism selected the initial low entropy state, though what that principle or mechanism might be remains unknown. The cosmic arrow of time, the direction in which the universe expands, aligns with the thermodynamic arrow, but whether this alignment is coincidental or reflects a deeper connection is debated. The psychological arrow of time, the direction in which we form memories and experience causation, appears to be a consequence of the thermodynamic arrow, as the formation of memories requires entropy, increase in the brain, but the details of how subjective experience relates to physical processes remain in the realm of philosophy of mind. Quantum mechanics introduces its own arrow through the process of measurement or wave function collapse, where a quantum superposition appears to irreversibly reduce to a definite outcome, though interpretations of quantum mechanics differ dramatically on whether collapse is a real physical process or merely an updating of information, and on whether quantum mechanics ultimately requires time asymmetric dynamics, or whether the apparent arrow emerges from decoherence and the growth of entanglement with the environment, the geometry of space-time on the larger scales, the global topology and shape of the universe, remains imperfectly known despite decades of observational cosmology. Observations constrain the spatial curvature to be very close to zero, consistent with a flat universe as predicted by inflation, but they do not determine the topology, whether space is infinite or finite, whether it wraps around on itself in complicated ways. A flat universe could be infinite, extending forever in all directions, or it could be a flat 3 torus, wrapping around in all 3 directions like a 3-dimensional version of the classic video game Asteroids, where exiting one edge brings you back at the opposite edge. Searches for topological signatures in the cosmic microwave background, looking for matching circles where the observable universe wraps around, and we see the same structures from different directions, have not found convincing evidence for finite topology on scales smaller than the observable universe, but they cannot rule out topology on larger scales, or more complex topologies that do not produce simple matching circles. The question of whether space-time itself is finite or infinite Whether the Big Bang was a singular event creating all of spacetime, or merely a phase transition in a pre-existing or eternally inflating spacetime, whether our observable universe is all that exists, or is one bubble in an infinite multiverse, lies at the boundary of science and metaphysics, potentially forever beyond the reach of observation, yet inextricably connected to our deepest theories.